So suppose we have standard deck of 52 cards and 12 shuffled, and you do this with replacement. So it's like you draw a card, and you put note what it is, and then put it back in the shuffle. You draw another card. So because then I'll have primitive trials, right? Trials will be independent. Now just that has to be number of bases. Well, then we could have even more. It's just 5 numbers. Okay, then X would be binomial, right? N would be 10. So this, that would be the problem. Maybe the problem is find the probability. Okay. So you do to the problem, you recognize, oh, looks like it's binomial, right? It's going to be trials, N is 10, P is the probability of base. So that would be 13. Probability of 5 bases. And then the only thing you'll barely use is the distribution function. In other words, if we'll have this notation, this is what you would have in the table. Okay? But you want the probability of 5 aces, so how would you get it with this? Well, go out to 5, right? And then subtract off out to 4. So this is less than or equal to 5 aces. Right. That includes 0 through 4. And have that. It's subtracted. Okay. Any questions on that notation?
You're saying the probability of 5 aces, why are you lesser or equal to 5? You are just trying to find 5 aces, not.
Yeah, but my notation is less than 1 through 5. That's the notation you're stuck with, okay? That's the notation of a table. Almost all tables are distribution functions. As you'll see, that's the things we really use in statistics. So you have to go out, this will go 0 through 5. And this will subtract off 0 through 4. So the notation is correct. It'll give you the correct answer. And if you were running R, that would give you a number. Okay? Now we could have the many-tab notation too, but the many-tab notation, as you'll see, you can't write down because it's clicking. Or you can write down the commands, but you would never want to. It would be horrible for a museum. You'd have to have CDF. You'd have to have CDF 5 semicolon binomial, 10 and 113. See, that's main tab. These are the commands. This to this. And you better store it in constant. And you'll have to make, you can't do 1/13. Somewhere. don't need those, three commands in Minitab to get this coming. So that's why we'll just pick on this notation. But any questions? For instance, maybe what's the probability of getting at least 7 aces? At least 7, and 7 or more. Well, we have to get the complement. Okay, so it's 1 minus the probability of x is greater than 6, right? Either x is greater than equal to 7 or it's less than 7. Strictly less than 7 for a binomial means less than or equal to 6. And now you have the notation, right? Now you can look it up in the table. Any questions on that notation? See, in another class, I would just invent notation for this and use it. We don't have to, we'll just use the one notation. So if you've downloaded it already, you can do it. And again, we'll introduce Minitab next week, so I mean, if you really have trouble with R, you don't have to worry about this class. Except you got to use that notation. The other one we talked about, where we have some notation is a voice line. Use a chocolate chip problem. That's all that's a voice line. That's approximately the number. What's the number of chocolate chips? Find the probability of a Lily cookie, and that would be a cookie with 10 or more chips. Someone said if you want a cookie, and they have this box of cookies, and you always look for the one with the most chocolate chips. Well, this would be, you'd have to assume here it's approximately cosine, okay. If you want 10 or more, again, you would look at the complement. The complement is this. And then that would be a table lookup, right? And the table for the quiz would be P cosine, right? 9, and then we have to put in lambda, which is 6. And yeah. Here's another good Poisson one. We have coyotes around, right? A couple of years ago in the neighborhood, before I put you off to sleep, I heard this hotline. And we finally figured out it was coyotes. So
Here's a Poisson problem, number of, well, maybe, probably a good one would be something like number of female coyotes in a couple square acres. You would have a unit size, I don't know what they would use. And then that would be Poisson, right?
Well, not, probably males would be better. Coyotes are probably like, well, I'm not sure, I don't know too much about coyotes. But the males usually mark their area, right? They'll fight another male that comes into it. So we might pick out a certain area and then a number of male coyotes in that area. That might be of interest in the models.
That makes sense because in a small area, there's not going to be 2 male coyotes instead of fighting. So it'd be approximately this.
Okay. You try to estimate the average number of coyotes. It's maybe capture and recapture things. Okay, any more questions on that one? Are we up on the notation? Okay. Any questions on the normal? Did you go over some of those normal problems?
I can get to that. I don't know why I lost it.
Just acceptance. Okay. It's just then a normal problem, and then solve it. How about, do wave this time, suppose the wave. Everyone knows about is normally distributed approximately. Standard deviation of 15. And then let's find the probability. We don't know wave over 200 pounds. Say 20. Well, to solve this, x would be normal, right? And the mean would be 170, standard deviation would be 15. We should square that. Be careful with the notation, it's usually variance. Okay. Certainly draw a picture if it's normal, okay, so you don't make a dumb error. You want that area there, right? Here's the mean. And you want the area to the right of 2. Again, you'd have to do complement, right, because it's the area to the left. And in this class, we could just use P norm, period. Right? You don't have to do a z-squared. But if you want to use the table in the back, you'll have to do a z-squared. So let's do it both ways. Okay. This is a problem on the exam, because they say, well, it's the complement, right? Now this is continuous, so it's not less than or equal to 199 or something. It's less than or equal to 200. In fact, the probability x is equal to 200 is 0, right? For all continuous models, the probability that x is equal to a value is 0. There's no area under the curve over 170. That's a continuous model. So definitely it's just this. Right? You can put less than or equals there if you want to. It's the same thing. It's not true for the binomial Poisson. Okay. But then once you have that, you'd say, oh, it's just P norm. 200, right? And then the mean's 170. Standard deviation is 15. Okay. But maybe you want to use a table in the back, so what you want to do is, and then just turn these to z-scores, right? It goes into 0, and this one will be 200 minus 170, 15. And 2. So then but the table in the back will give you this area. So it'll give you the area to the left. If you look up at the table, it's 9772. So one answer would be this answer would be 1 minus. And you're doing the same thing, right? 0 to 0. Any questions on that? On the normal? Normal will be handy because a lot of our test statistics are in terms of normal. Now, the normal is not that good for data because this probability of outliers is so small. So in the book, I put some other normal models in. Let's just talk about them briefly. I don't know this one. Oh wait, let's do one quantile problem too. And then let's do a mixture problem. Okay, quantile problem. Let's find the next. Let's find the 90th percentile. What is this? That means you want to find this value C. So there's only 10% here, right? 9%. So really, there's a command in R which will give you that quantile without any more work. Okay, it's just Q for quantile. And you have to get to the area to the left. So at least it's like it's the inverse of the P command. Really. And you've got to put the area to the left, then the mean, and then the standard deviation. But if you want to use a table in the back to solve this, so you get a number, you want to use R. Just do the same thing over. Okay. Remember the transformers, that's the z-square. And then in the table in the back, you can approximate this. You just get as close as you can to 0.9 with 3 zeros of the table. If you look through the table, it looks like 1.28 will do the trick. Then you can solve for it, and then C would be 15 times 1.28 plus 1/7. Okay, any questions on that?
Yeah. Is your argument under Q norm it says 0.9, 170, and 15 is your variance or standard deviation?
Standard deviation. This is sigma.
Okay.
I'm not sure why that notation. I mean, that's the normal
To
notation.
compute a z-score,
Pardon me?
is it over? It's over standard deviation. Okay.
Yeah, right. You standardize the standard deviation, not the variance. X is normal mu sigma squared if and only if z equal x minus mu over sigma. Normal 0.
So that's the question, I guess. For the command Q normal, is it the variance or the standard
It's
deviation?
always a standard
Always the
deviation.
standard deviation.
Okay?
So for the binomial, it's like a variance. But for the normal, it's standard deviation.
No, for the binomial, it's just n and p. Okay? It's just the parameters. It is for the normal too. I don't know why well, Minitab does that too. It's a standard deviation. It's that capital N notation. Yes. Right. I don't know why I introduced variance. I've never seen a book that uses standard deviation. So that must be wrong in this. Okay, how about a mixture problem? You're in a room and someone tells you there are 20 people in this room and 16 of them weigh over 200 pounds. So how I am the probability of weighing over 200 pounds is 2%. So you know that's pretty bad.
Michigan.
So it's really a mixture, right? Probably the main variable of interest is the number of people over 200 pounds. Now you have to assume these people are sort of independent of one another. He's got to have new terms. All right. And, the probability of success on each probability of that normal. So here you might say, then I'll use a different letter. That's y. Okay, that's the weight. So we know x is normal. So here the probability of success actually this one here. That would be the probability of success. Right? Now the question was, is this odd? It's probably 16 or over if we think that we have them. You'd just like to find the probability of y greater than 16. It's extremely small. And then you could do this like this, right? P. So we can find that. Zero to six spaces. Any questions on that problem? There's just no mass left, 0 to 6 spaces.
So where did you get the 0.0028?
We just solved it.
Yeah, I have to thought that was.
Here's a normal problem. You want to find a probability estimate, comes out to 1.2. So that would be successful. Probability of success.
You can just give us all A's, we'll keep that. It's a lot less work for you.
My father, just do more A's. How about some other continuous ones? Well, let's just go through a few that are in the book. It's a double exponential. It's often the Laplace. Called the Laplace, and it's just got two of this. Okay. Now, the density, again, that's not that important. The density is of this form. And see, so it's the tails are like coming down as an exponential, hence the name double exponential. That's just the absolute value. Remember the normal. We like that 1/2 in there, but that's not going to slow x squared down. This is coming down much faster. So if you put a normal on top of an exponential, the tails will be something like this. The tails are going to die much quicker. There's much more weight out here for an exponential. And you can go through the probability of an outlier, and it's like 0.06. The normal, it's what, 0.007, and for the double exponential, the loss comes out to 1.06. So in a sample of 100, you'd expect about 6 outliers in the Laplace, whereas for the normal, you hardly somewhere about 1. Another one that's logistic, just the outlier. Something in between is a logistic. This one, the logistic is mound-shaped. It takes a very large sample size to differentiate between a logistic and a normal. But the tails are slightly heavier, okay? Well, you're 3 times likely to have an outlier with the logistic, right? 0.022, 0.007. What's its density? You'll never believe this, but it's this. Don't copy this down. This beast looks just like this one. It just so surprising. And then I threw in the Koshi too. Koshi is mound-shaped. Koshi has 16% out. It's huge. It has very thick tails. So again, this would be like a normal. This would be Koshi. The Koshi has such thick tails it doesn't have a center of gravity. It's just too much weight. So we can actually start talking about inference, but I don't think it would. Let's talk a little bit about independence. Often you do have univariate data. You're looking at univariate data. You might have an experiment where you get a string of information, but you only use a few pieces of it. So you're thinking univariate, but often you're collecting data on a couple groups, right? You're always interested in relationships between variables. If X is large, is Y large. Okay? If a person weighs a lot, is he tall? So you want to somehow convey that information as a relationship, right? And again, for the discrete case, we can actually go through everything. Okay? And what we do in the discrete case, we can look at 2 discrete variables and we can talk about the joint distribution. It's no biggie. Right? And the concept of independence is very straightforward. So, here's a dumb experiment, just to get us started. Well, no, in fact, this is not a dumb experiment. This is a Scottish heritage. Scottish school children, and we've measured hair color and eye color. And we want to know if there's a dependence between eye color and hair color. We sort of know that now, right? Well, we do know that now, right? Because we know genetics. This data was collected in the early 1900s, long before they discovered DNA. It wasn't until the 40s and 50s. So, is there a relationship between hair color and eye color? Okay. So we need to talk a little bit about that. And we can do it with the discrete model. It's a little bit tricky. This is an example where it is tricky. So here's my big example. I have this spinner with the numbers 1, 2, 3 on it, and I spin it twice. Right? And then x will be the sum of the numbers spun. So if I like spin 1, 1, x will be x is 2. And then y is the absolute difference. So if I spin 1, 1, y will be 0. It's sort of a dumb example, but these turn out to be dependent variables. They'll have no correlation. Okay. Well, then I can go through all the spins, and that's all the spins, right? There are only 9 possibilities. If you count down here, there's the 9 possibilities. You can spin a 1, 1, 2, 2, a 3, 1, 3, 2, down to a 3, 3. And then for each of those, you just calculate x. And then calculate y. X is just the sum and y is the absolute difference. Okay. Then you can go back and you make this table. This is a table. Now we're collecting. The range is like a table, right? X could be 2 through 6. That's the only possibilities, and y could be 0, 1, and 2. Okay. And then when x is 2, y is 0. That's the only one, and these are all equally likely. We just spin the spinner. The spinner is completely fair. Okay. So each of those come up with probability 1/9. So this occurs with 1/9, and there are no other occurrences. Right? And then when x is 3, y is 1, where y is 1. So that happens 2/9 of the time. And then we can fill in the other ones. That's called the joint distribution of x and y. I shouldn't have these things. But you can get the marginal distribution too, right? What's the probability x is 2? Well, you don't have to go back to this. It's right here in the table. X is 2, and y is 0, or x is 2 and y is 1. That's the only time x is equal to 2, that top row there. And those are disjoint events. So the probability x is equal to 2 is 1/9. Those are called marginal probabilities, but they are the distribution of x. So x equals 3 2/9, and you just add these up. So there's the distribution of x. And I think that's your first vision in this class of the central limit theorem, right? So the number is fine. That's the distribution of the number spun. It's like you add these two together and you don't get it flat, you get mound-shaped distribution. Right? It goes up in 3 9s. So it goes 1 9, 2 9s, 3 9s. That's the central limit theorem. in the wings. It's coming. We'll talk a little bit about that. And then we can get the distribution of y. This one is sort of odd. Probably haven't really thought about that. Why in the hell would you ever think about this one? It's 3/9, 4/9 centimeters. Okay. Okay, so on Tuesday we'll finish that and we'll talk a little bit about the central limit here. And then we're ready for integers. A bit too long. Okay, so you ready for the quiz?
Half one, half the other, whatever you